Good morning. Thank you to the organizers for inviting me to come along and speak to you today about post-quantum crypto. So just to give you an idea of the context, to remind you how we use crypto on the internet, let me talk about how key exchange is used on the internet. There are a few acronyms that are used for the protocols. You might have heard of SSL, the Secure Sockets Layer. Sometimes we call that TLS, Transport Layer Security. Those roughly mean the same thing. And they're often used in the context of HTTPS. That's web traffic delivered over SSL or TLS. So when you're browsing your favorite website on the internet and you look into the top left, hopefully you see this green icon with a lock and HTTPS. So when you click on that, you find out some information about the connection you're visiting. Okay? And it tells you the connection is secure. That's good. And it tells you the name of the website you're visiting. And it also tells you a little bit about some of the cryptography that's being used there. Okay? And if you click a little bit further, you also see something like a certificate, the digital identity of the site you're visiting. So let's take a little bit of a look at the cryptography that's being used here. So there's this string here, the connection string, which has a bunch of cryptographic algorithms in it. Okay? And to remind you, we have two different types of cryptography being used whenever we establish a secure connection. We have public key cryptography, and we have symmetric cryptography. Okay? So some of the algorithms in that list, the public key algorithms, are the RSA signature algorithm and elliptic curve Diffie-Hellman key exchange. Those are used to set up our secure connection. And then once we've established that secure connection, the other two algorithms used, the symmetric cryptography algorithms, are AES encryption and the HMAC algorithm for integrity. Okay? So those are the algorithms that are being used in the connections you use day to day. So just to detail a little bit more how that works, so when you want to establish a connection to a website and send a message, well, we're going to use authenticated key exchange to establish our secure connection, and then symmetric encryption to deliver our message. Okay? So Alice wants to send a message to Bob, okay, and she's worried about various adversaries listening into her connection. Okay? So of course, she's going to encrypt that message with a key to create a ciphertext and send that ciphertext over to Bob, who's then able to decrypt. Now, before they can do this, they need to actually have a key. They have to use the same key on both sides for AES, so they need to have a key established between them. And in order to establish that key, they're going to use a key exchange algorithm. And in the example that I showed you before, it was Diffie-Hellman key exchange. Okay. Now, this Diffie-Hellman key exchange isn't authenticated, so to prevent man-in-the-middle attacks, we need some additional authentication. And what we had before was authentication using RSA digital signatures, using a signing key and a verification key. And the way each party gets a copy of the other party's public key is using a certificate. Okay. So all of those pieces together, those comprise our secure channel protocol, TLS. So that's the context that we're working in. Okay. Now, coming back to our cryptographic building blocks, we've got our public key cryptography and our symmetric cryptography. And our public key algorithms like RSA or Diffie-Hellman are based on number theoretic cryptography. So RSA is based on the difficulty of factoring, elliptic curve Diffie-Hellman based on the difficulty of computing discrete logarithms. And I guess as all of you know, these are problems that could be efficiently solved by Shor's algorithm on a quantum computer. Okay? And so these are the parts of cryptography that we're most worried about being broken with the advent of quantum computers. The algorithms on the right-hand side of the screen, the symmetric crypto algorithms, more or less can't be efficiently solved by a quantum computer. They can be sped up a bit by Grover's search algorithm, and certain modes of operation we've recently found out are vulnerable to attacks by quantum computers with superposition queries, but more or less we're fairly confident in our symmetric algorithms. So for people building classical cryptography, we need to have replacements for these public key algorithms. Okay? And the question then becomes, when will a large-scale quantum computer be built? And all of you know that the answer to that question much better than I do, so I can only reproduce a couple of slides that the quantum crypto and quantum computing community have created. So there's a slide on the stages to building a large-scale quantum computer that we need to be able to do operations on single qubit operations on physical and then multiple physical qubits. Eventually, that'll bring us to error correction, and then having memories with lifetime longer than just a physical qubit's lifetime, allowing us to create logical qubits at eventually a fault-tolerant quantum computer. Now, even still, this isn't a timeline, but some people in the quantum computing community have put their name on the line and given estimates on when we might have a quantum computer. So here's one estimate. I estimate a 1 in 7 chance of breaking RSA 2048 by 2026 and a 50% chance by 2031. RSA 2048, these are the public key sizes we use on the internet. Now, whether you should believe this quote or not is entirely up to you. Mike Moscow is my PhD supervisor, so I'm obliged to believe him. But anyway, this is one estimate. So in the classical crypto community, there's been an ongoing effort for some time to build quantum-resistant cryptography. And we call this post-quantum cryptography. So in academia, we've had a series of conferences on post-quantum crypto since 2006. They were every other year for the first few years of the conference's life, but now they are running every year because of increased interest. And there were 300 or 400 people at the Peak of Crypto earlier this year in the Netherlands. There's a classic textbook. So in academics, we've been focusing on this more and more. Post-quantum crypto has also come to the attention of governments. So the NSA, in 2015, made this rather mysterious and unexpected statement that they'll initiate a transition to quantum-resistant algorithms in the not-too-distant future. And many people watching the NSA apparently were very surprised by this statement, because they don't usually say things like this. And then last year, NIST, the United States National Institute of Standards and Technology, which for our cryptographic community standardizes many algorithms, issued a report saying that they were planning a transition to post-quantum crypto as well. And so that's one of the big things going on in the post-quantum crypto community right now, the NIST post-quantum crypto project. So it was announced last year with a deadline for submissions coming in November 2017. And so they're asking for submissions on digital signature algorithms, public key encryption, and key exchange, and then plan to spend 3 to 5 years reviewing these algorithms through a series of workshops with the hope of having draft standards ready by 2023 to 2025. Okay? And this follows somewhat follows similar NIST competitions for hash functions and symmetric encryption algorithms. But one difference in the NIST post-quantum crypto competition is that it's not quite a competition in the same sense. For the advanced encryption standard, about a decade and a half ago, they picked one winner. And for the SHA-3 competition, they picked a winner. But for the NIST post-quantum crypto project, their intention is actually to select a couple of different options, and not primarily to pick a winner. And perhaps this reflects that post-quantum crypto is not quite as well developed as other things that the NIST has standardized. We don't understand all of the algorithms and their security properties quite as well as other things we've worked on in the past. And so the goal of the NIST process seems to be to identify several options that could be used, even if we don't have an ideal one with as much confidence as we would like. So that's the NIST timeline. So is it going to be enough? Will it mean that we have post-quantum crypto ready in time? Okay? So NIST started this post-quantum crypto project in 2016 with a deadline in 2017. And as I said, with a goal of having standards ready between 2023 and 2025. And if you go back to a few slides earlier, I mentioned a timeline for quantum computers. Mike Mosca said some 2026 to 2031. A document from the European Union estimated 2035. So you look at this and say, all right, we've got post-quantum crypto ready before estimates for quantum computers. Okay. Well, is this soon enough? It turns out it takes a long time to implement and deploy cryptography in practice. So if we look back at a previous example, hash functions. So SHA-1 is NIST's first standardized hash function, and they standardized it in 1995. Okay? And it was all right, but a few years later, they standardized a better one, SHA-2 in 2001. Okay? And this was good because in 2005, at Crypto 2005, there were some weaknesses identified in SHA-1 that were better than theoretical, not a complete practical break, but better than theoretical. And so that said, we probably should be transitioning to SHA-2. Okay? Well, it took until January 2017 for web browsers to stop accepting certificates with SHA-1 hashes in the signatures. Okay? So it took 16 years from when the replacement was standardized until it was deprecated in widely used software. And that came just in time because last month at Crypto, the first full collision for SHA-1 was announced. Okay? So it took 16 years to replace or to deprecate old crypto and replace it with new crypto. So that makes the NIST post-quantum timeline for standardization look a bit tight compared to the potential advent of quantum computers. Anyway, so that's kind of the big exciting thing happening in post-quantum crypto, and through much of crypto these days, the NIST post-quantum crypto standardization process. So in the rest of the talk, I'm going to tell you a bit about post-quantum crypto. Okay. So what I mean by post-quantum crypto, or what some people call quantum-resistant algorithms, is classical cryptography where there's no known exponential speedup for solving the crypto system. And there are several different families of mathematical primitives that seem to be useful for building post-quantum cryptography. 5 widely accepted ones in particular. 2 of them are hash-based cryptography and code-based cryptography. So hash-based cryptography dates from the earliest days of public key cryptography in the 70s, and we're able to build signature schemes directly from hash functions. The other fairly old form of post-quantum public key cryptography is code-based cryptography based on error-correcting codes. And there's the McLeese cryptosystem, also from the earliest days of public key cryptography. At the time, though, the McLeese cryptosystem resulted in much larger public keys and slower operations than RSA or Diffie-Hellman. And so it didn't see as much adoption as the number-theoretic-based ones. Then more recently, we have 3 other families of post-quantum crypto algorithms. There's multivariate crypto, which is based on the difficulty of solving multivariate quadratic equations. There's lattice-based crypto, where the crypto system relates to an underlying hard problem on lattices. And the most recent form of post-quantum crypto, isogenies-based crypto, where we have a certain problem on elliptic curves, namely the isogenies between elliptic curves that allows us to create public key crypto. Okay. Now, all of these are classical algorithms, classical post-quantum crypto algorithms, that might fit into the larger family of what we would call quantum-safe cryptography. The other side of quantum-safe cryptography being what many of you do, quantum crypto. So quantum key distribution, quantum random generators, quantum blind computation, and so on. So we have these 2 families of potential solutions for resisting attacks by quantum computers. But my task today is just to talk to you about post-quantum crypto. So the overall research agenda in post-quantum crypto, well, we need to design better post-quantum schemes, more efficient based on the problems we have, or identify new problems. We need to classify and characterize the classical and quantum attacks against these schemes so that we understand how difficult the problems actually are. Once we know the best attacks, we can use that to pick parameter sizes. If we want to achieve security against an adversary with a certain runtime, then the attacks tell us how big our parameters need to be to resist those attacks. From there, we can develop fast, secure implementations and eventually integrate them into the existing infrastructure. And because of the close timeline we need to achieve this agenda, we actually have to be working on all of these at once. So in today's talk, I'm going to talk to you about one particular family of post-quantum crypto algorithms, namely lattice-based cryptography, specifically using the learning with errors problem. I've picked this one to tell you about, A, because it's the one that I understand best, but also because I think it's the simplest to understand. It's also a very competitive and compelling algorithm for practical implementation. So I think there's a lot to be learned from it. I'll talk a bit about the transition to post-quantum crypto and a software project that I'm involved with on trying to make that more practical. So first off, the learning with errors problem. Okay? So I'll give you an idea of the mathematics behind it. It's really quite straightforward. So here is a problem solving a system of linear equations. So if I gave you, well, if I took a matrix, the blue matrix on the left, and I multiplied it by some secret vector to get a result, and if I gave you the blue matrix and the result, and asked you to find the red secret vector, you could easily do so. If you've passed my first year linear algebra course, you know to use Gaussian elimination, so that's how we can solve that system. Okay? So this is not a good problem for cryptography because most first-year students can solve it, although not necessarily in the context of an exam. But most of them can solve it, so this is not a good crypto system. Okay? But it turns out we can make a very small tweak to this and come up with a problem that seems to be hard to solve. Okay? Again, this is starting with a random matrix. I multiply it by a secret vector, and this time I add a small noise vector to the result to get the final vector. Okay? So if I now give you the two blue elements, the matrix and the final vector, and ask you to find the red secret vector, this turns out to be a hard problem. Or at least for appropriately chosen parameters, this seems to be hard. And we call this the learning with errors problem. Or more specifically, the search learning with errors problem, because it's about searching for the secret red vector. Now there's another version of this problem called the decision learning with errors problem. Okay? Here again, I take a blue matrix, multiply it by a red secret vector, and add my noise. And it turns out the result that I get seems to look random. So in the decision learning with errors problem, I either give you the real result, or I give you a uniformly random vector and ask you to decide which. And the decision learning with errors problem is quite useful for building cryptography because we like things that look random. We can use those random looking things as keys. So these are the two main problems in lattice-based cryptography. Now, to say them a little bit more formally, in the search learning with errors problem, we have some parameters n, m, and q, which are about the size of our system. We have two distributions over the integers, chi-s for our secrets and chi-e for our error vectors. And then we sample a secret vector s according to our secret distribution. Sorry, when I say secret distribution, the distribution itself is not secret, just that it's used to generate secrets. And then we sample a bunch of uniformly random vectors and noise e, and we compute the inner product of each of those vectors plus some noise. This is just our matrix multiplication plus adding a vector from the previous slides. And the search learning with errors problem is given the vectors a and the results b, find the secret vector s. And the decision learning with errors problem is quite similar. We have the same setup, our same distributions, and a sampled secret vector s. This time we have two oracles that the adversary interacts with. The real oracle, O sub chi es, and what this does is it creates real LWE samples, picks random vectors A, and produces B's according to the way it's supposed to. Or there's a uniform oracle, U, that just generates vectors uniformly at random. And our adversary is going to interact with one of these two oracles, but doesn't know which one. So the decision LWE problem is to distinguish the real distribution, vectors from the real oracle, from the random distribution, vectors from the random oracle. So these are our two main problems. Now, in both of these problems, I mentioned the error distribution. And this plays a critical role in the security of our system. Okay? And usually in lattice-based cryptography, we end up using discrete Gaussians. So I've written down the distribution functions there. For the purposes of the rest of this talk, we don't really have to know those, but I've put them up there for completeness. One important thing is that the width of our distribution be sufficiently wide. So there's an error parameter alpha, which tells us the width of the distribution. And in order for security to hold, we need to have this width to be sufficiently large. Now, that's the error distribution. We also have the distribution of our secrets. We have several choices for that. We could use uniformly random secrets, but it turns out it's safe to also use short secrets. Originally, we did take secrets from the uniform distribution, but now we end up using short secrets, the same distribution as the error distribution. And there's a tight reduction between these two distributions, or between the LWE problem using these two distributions. So either one is equally secure. We like using the short secrets because it decreases our error probability, our failure probability for encryption. So in the examples I've shown you, I've shown you this small matrix here, a toy example. But in practice, we have to use much larger parameters in order to achieve sufficiently large parameters for security. So for LWE, we might use a matrix that's 752 rows by 8 columns, and each entry of the matrix being chosen from 2 to the 15, say. Okay? So that ends up being a fairly large matrix, about 11 kilobytes to represent in total. And that's quite large communication requirement compared to the crypto systems we're used to today. RSA 2048, mentioned at the beginning of the slide, only uses 2,000 bits. So to have to send 11 kilobytes to establish a secure communication channel would be quite unfortunate. So we also have a variant of the learning with errors problem where we introduce a little bit more structure that allows us to save on communication. And this is the ring learning with errors problem. Okay? So in the ring learning with errors problem, we're going to have a simplified view of the matrix. Okay? So imagine that rather than using a uniformly random matrix, I just pick the first row of the matrix uniformly at random, and then construct every remaining row of the matrix as a cyclic shift of the row above. Okay? And, well, rather than doing a perfect cyclic shift, I'm going to do a special wrapping rule, so wrap around with negative numbers each time. And if I do this, then I don't actually have to tell you the whole matrix. If I want to communicate with you, I just have to tell you the first row, and you can reproduce the rest of the matrix. This is the basic idea of the ring learning with errors problem. Now, there's an equivalent representation of this working in a polynomial ring. So we have a ring of polynomials modulo a fixed polynomial, and then all of the coefficients are also reduced modulo a prime. Okay? So in the ring learning with errors problem, we pick a random polynomial, multiply it by a secret polynomial, add some noise to get the result. And then given the two blue polynomials, the search ring learning with errors problem is to find the secret red vector, the secret red polynomial. Okay? So an analog of the matrix-based one we saw earlier, but now with a more compact representation. So finally, we have our complete set of problems. So we have the search learning with errors problem and decision learning with errors problem based on multiplying matrices and adding noise. And then we have the ring forms of that, multiplying polynomials and adding noise. And we can do each of these problems with or without short secrets. So these are the main families of problems that we're going to try to build cryptography out of. Now, here we've got a few different ways of classifying these, but there's the search problems and the decision problems. And one nice thing in this family of problems is that we actually have an equivalence between the search problems and the decision problems. So it's a fairly straightforward exercise to show that if the search problem is easy, then the decision problem is easy. If you have to decide whether there's something random, well, you could just use your search oracle to solve it, and then check and see if it was actually computed randomly or not. So if we can solve the search problem, we can definitely solve the decision problem. But what's nice in this family is that the reverse is true. If the decision problem is easy, then it turns out that the search problem can be solved efficiently as well. It's a little bit more of an exercise to go through. It requires multiple calls to the decision oracle, but it can be done. The basic idea is that we can work through the vector, the secret vector, one component at a time and figure out what each component is without having to solve the entire thing at once. So we solve one component and then move on to the next component of the vector and so on. And so this means that when we build a crypto system out of learning with errors problems, we can use the search problem or the decision problem, and we have more or less the same difficulty for the adversary. And this isn't quite the case in our traditional classical cryptographic algorithms. For Diffie-Hellman, for example, we have an implication. If you can solve the computational Diffie-Hellman problem, then you can solve the decisional problem. But the reverse isn't known to be true. Now, also in the lattice-based world, we have another problem called the NTRU problem. This dates from the late 90s and also is a problem on polynomial rings with some noise. But I'm not going to spend much time on this problem today. I just wanted to mention to you it has a similar structure to the ring Lerner-Theres problem. Now, I've used the term lattice-based a few times, but all of the problems that I've talked to you are about multiplying matrices and adding noise. So I have to justify to you the use of the term lattice-based. Okay? Lattice-based comes up because the difficulty of LWE can be related to the difficulty of solving a lattice problem, namely the worst case shortest vector problem on a lattice. And there's a polynomial time reduction between these problems. So let me remind you what a lattice is. Okay? So for a lattice, we start off with a basis of linear independent vectors, b1 up to bn, for some space zq to the n. And a lattice is the set of all linear combinations of these vectors. But the key difference between a lattice and a vector space is that for a lattice, we're only taking integer linear combinations rather than real linear combinations. So this will identify some subset of points in the plane. And a key metric on a lattice is the minimum distance of a lattice. This is defined as the length of the shortest non-zero vector in the lattice. In 2 dimensions, this looks like it's quite easy to solve. You can draw a graph of the lattice, and then you just look for the point on the lattice that's closest to the origin. But when we try to do this in larger dimensions and with an arbitrarily complex lattice, it becomes much more difficult to figure out what the shortest vector is. And in fact, this is called the shortest vector problem. So if I give you the basis for a lattice, and I ask you to find the shortest vector, we call that the shortest vector problem. Now, a related problem to the shortest vector problem that ends up coming up in our proofs is something called gap SVP, the decision approximate shortest vector problem. Okay. And so here, again, we start off with the basis for a lattice. And the task in the gap shortest vector problem is to decide whether the shortest vector in the lattice is below a certain value or above a certain value. Okay? So is it less than or equal to 1, or is it greater than gamma, say, for some factor gamma? So this is asking you to just approximate the length of the shortest vector. And this approximate shortest vector problem is what we use to give the security of the learning with errors problem. So a few slides ago, I had this picture here showing that the decision learning with errors problem can be polynomial reduced, polytime reduced to the worst case gap shortest vector problem. Okay. And I'll just give you the statement of that theorem. This is proved by Oded Regev in 2005 when he first introduced the learning with errors problem. And the main points to take out of this are that solving the decision LWE problem is at least as hard as quantumly solving gap SVP and some other lattice problem called SIVP. Okay. There's a bunch of stuff in here about parameters. One critical parameter choice is right here. I think I mentioned to you before that the width of the distribution, the width of the error distribution in our LWE problem played a certain role. And here you can see that it has to be above a certain threshold. Okay. So this is a polynomial time reduction, and that's great. That gives us a heuristic confidence that the learning with errors problem is hard if the underlying lattice problem is hard. Now, unfortunately, it's a very non-tight polynomial time reduction. It's an order n to the 13 reduction. So that doesn't exactly tell us as much as we would like about the difficulty of instances in practice, but it does tell us, at least heuristically, that they're hard from a complexity perspective. So if we wanted to have an LWE-based crypto system, we know that we can relate it to the difficulty of solving a lattice problem. The next step would be, how hard is it to solve a lattice problem? Okay. So there are several different algorithms for solving shortest vector problem that have been studied in the literature for a while now. And I've listed a few of them here. The LLL algorithm, which probably you've heard of, runs in polynomial time, but it doesn't find very short vectors. The approximation factor of the vectors it finds is exponential in n, or nearly exponential in n. Okay. There are other algorithms that can find short vectors with a polynomial approximation factor, but those take exponential time or exponential time in space. And then there is an interpolation between those where we can have a sub-exponential approximation factor with a corresponding sub-exponential runtime. We know a little bit more about the complexity of this problem. If the approximation factor has to be around square root of n, then the problem is in NP intersect co-NP. And if the approximation factor has to be sub-polynomial, then we know that sublinear, in fact, we know that the problem is NP hard. In cryptography, we end up using approximation factors around n. And so this doesn't actually put us anywhere on the slide. As is usual in cryptography, the parameters that seem to be useful in practice don't really lie in the realm where we have complexity theoretic reductions. OK. So based on these algorithms, even though they aren't exactly applicable to our parameter space, we can still estimate the runtime of solving lattice algorithms and use that to pick learning with errors parameters. And there are two approaches that people are using in the literature. One approach is based on reductions. So we know that LWE relates to an underlying lattice problem. So we calculate the runtime required for the underlying lattice problem. Then we trace through our end of the 13 reduction, and we pick parameters for our LWE problem based on that. Okay? That's going to result in quite large LWE parameters because of this very non-tight end of the 13 reduction. An alternative approach that people are using is based on cryptanalysis. So they look at what the best known algorithms are for LWE rather than the underlying lattice problem. And it turns out that the best way of solving LWE does indeed happen to be solving the lattice problem. So they pick parameters based on the best known LWE solvers. And that allows you to use smaller parameters. And you'll see both of these approaches in techniques that people are proposing for use today. All right. So how big are the parameters that we end up with? Well, if you follow the cryptanalytic approach and apply it to ring-LWE, this cyclic structure allows you to save communication, and you'll end up with parameters that are about 4 kilobytes in size. So each party has to send a 4 kilobyte public key in order to establish a secure channel. If we do that for the matrix form, plain LWE, then we have to send larger elements, which end up being about 11 kilobytes in size. So each party has to send 11 kilobytes, 22 kilobytes total to establish a secure communication channel. So those are what we might get for the particular problems we've talked about. Now, if ring-LWE is smaller, more efficient communication, then you might ask, well, why would someone even consider this slower, bigger LWE problem? And the reason is because it leads to a slightly different lattice problem. Okay? And in particular, the underlying problems are distinct whether they're about generic lattices or ideal lattices. Remember, in ring-LWE, we added this structure, this cyclic structure to the matrix, which could be then represent in a ring. Okay? So ring-LWE matrices have additional structure. And whenever we introduce structure in cryptography, we tend to make things easier. Or at least there's the risk that we made things easier. And for ring-LWE, when we relate it back to the lattice problem, we see that this additional structure means that it's now a lattice problem on a type of lattice called an ideal lattice. Whereas these unstructured LWE matrices, they relate to a problem on what are called generic lattices. Okay? So our underlying lattice problem also has more structure. I mentioned NTRU as well. NTRU ends up relating to a problem on ideal lattices as well, although a different type of ideal lattices than ring-LWE. Okay? And when we introduce this structure, and when we switch over to ideal lattices, there's this risk that we have now made the problem easier to solve. At present, the best known algorithms for solving ideal lattice problems are more or less the same as solving for generic lattices. There's a small constant factor improvement in some cases, but generally the problems seem to be the same difficulty for the algorithms we have today. Now, last year there was actually some progress on a quantum polynomial time algorithm for solving the shortest vector problem on certain types of ideal lattices. But that isn't actually applicable to ring-LWE. But this does show that in some cases, when we introduce this ideal structure, there's the potential for a more efficient solving algorithm. And so this is why people are also still interested in the plain LWE problem, because it may have resistance to attacks that take advantage of structure. Okay. But we'll see both ring-LWE and LWE systems submitted to the NIST proposal, and both have their compelling arguments. All right, so these problems serve as the basis for building cryptography. So I should probably tell you a bit about how we can actually build cryptography from them. Okay. So I'd like to tell you about a public key encryption scheme based on the learning with errors problem. And this was created by Lindner-Peikert in 2011. Okay. So for public key encryption, remember we need three algorithms. We need a key generation algorithm, where one party generates a public key and a secret key. Then there's the encryption algorithm, that the sender uses the recipient's public key to send a message by creating a ciphertext. And we have the decryption algorithm, where the receiver uses their secret key to decrypt the ciphertext and recover the message. So in this public key encryption scheme, it's going to be based on LWE. So in the key generation algorithm, we're really just going to generate an LWE instance. So the key generator, they're going to pick a random matrix A, multiply it by a secret vector S, add an error vector E to get a result vector B. And these two blue components, the matrix A and the vector B, are going to form the public key, and the red vector will be the secret key. So exactly as we had in the examples that I showed you at the beginning of the presentation. So that's key generation. For encryption, we had to say how to create a ciphertext based on the public key. Okay. So the sender has a copy of the recipient's public key. Okay. So the sender picks a secret vector S prime, multiplies it by the receiver's public key, adds some noise to get a ciphertext vector B prime. Okay. This actually looks just like an LWE problem, except I've done it in transpose rather than the original way. But it is just another LWE instance. So that's the first part of encryption. But there's no message actually here. This is just a bunch of random vectors. And so we actually want to be able to encrypt a message as well. So there's a second part of encryption. We take the other part of the receiver's public key, B, and also multiply it by the same secret vector S prime. That'll get us a single element to which we add a small noise vector and get a result. Okay. And this V prime result here, that's going to be a mask that we can use to encrypt our message. And it'll be a shared secret mask, so I'll show you on the next slide how the recipient is going to come up with the same value. Okay. So given this mask, the way that the sender encrypts the message is to take the mask. Well, I'm not going to just directly add the message. In fact, what's going to happen is that I'm going to add q over 2 times the message. So the message will be a single bit, and I'll multiply it by q on 2. So if my message is 0, I take and represent the ciphertext as v prime plus 0. And if the message is 1, then the ciphertext is v prime plus q on 2. Okay. And we'll see in a moment the role of the q on 2. It's going to allow us to do error correction. So this is how encryption works. The recipient's public key, A and B, are used in 2 ring learning with errors type problems to come up with a ciphertext B prime and a mask V prime. And then the V prime mask is used to encrypt the message. And the final ciphertext is B prime and C. Okay. So that's what the sender does. And now the recipient wants to decrypt. Okay? So the recipient receives the ciphertext B prime, multiplies it by their secret key, and that's going to get them a masked value. Now I've written V here instead of V prime because it's not quite the same shared secret, but I'll show you on the next slide that it's almost the same shared secret as the one that the sender used. And let's just, for now, assume that we indeed have the same shared secret. So the recipient will take the other ciphertext component C, subtract off the mask, and, well, if you remember, the ciphertext C was V plus a multiple of the message. So when I take C minus the mask, I'm going to indeed get a value left over, and I'm going to use a rounding mechanism to figure out what the message actually was. So if there was no noise, then we'd be left with either Q on 2 or 0. And if it was Q on 2, I would say the message was 1. And if it was 0, I would say the message was indeed 0. We're going to have some noise, and so we'll apply a rounding rule. If the result of C minus V is closer to Q on 2, I'll say that that decrypts to 1. And if it's closer to 0, I'll say that it decrypts to 0. This will be the recipient's copy of the message M prime. And the reason for this rounding and the reason for this Q on 2 encoding is because the mask values V and V prime are not going to be exactly equal. They're only going to be approximately equal. Okay? So if you remember, the sender computed their shared mask value this way. S prime times the sum AS plus E plus their own noise vector. Okay? And when we expand it out, we get this value here, S prime AS plus some noise. Whereas the recipient, they computed their mask value as shown here, the sum S prime A plus E prime, all multiplied by S. And when you expand that out, that's S prime AS plus some noise. So as long as these two noise components in parentheses are sufficiently small, then both parties have computed something that's approximately S prime times AS. Okay? So we just have to make sure that our parameters are picked so that this noise in parentheses on both sides is smaller than our error correction threshold, which in this case happens to be Q on 4. And it's possible to pick parameters that satisfy this and ensure that both parties can actually compute the same value on both sides. So that's how they're able to correctly encrypt and decrypt. And so from this, we have a public key encryption scheme. Okay? And we can prove that this encryption scheme is secure. In particular, it satisfies a property called indistinguishability under chosen plaintext attack. Here's the statement of the theorem here. And the main thing to take away from this slide is that it tells us that the security of this encryption scheme really is based on the learning with errors problem. So as long as the learning with errors problem is hard, as long as the advantage of an adversary in solving the decision learning with errors problem is small, then the advantage of an adversary in breaking the IND-CPA security of our encryption scheme is also small. I realize I didn't tell you what indistinguishability under chosen plaintext attack means. For those of you who don't know, it's a fairly standard definition of security for public key encryption scheme. It means that an attacker can't learn any meaningful information about a message, even given the public key of the recipient. So they're able to encrypt messages of their choosing. That's the chosen plaintext attack. And messages encrypted under this scheme should still be secure or indistinguishable. This is a widely accepted notion in the literature. Okay. So this encryption scheme is secure against these types of attacks. Now, this security notion is actually not the strongest security notion that we have. We have another security notion called indistinguishability against chosen ciphertext attacks, which is even stronger. This allows the adversary to also learn the messages corresponding to ciphertexts. And the encryption scheme I've shown you isn't secure against these types of attacks. Okay? And this is because the encryption scheme doesn't have a property called public key validation. Okay? So we can't actually tell if a public key is well formed. And so when the recipient decrypts a message, decrypts a ciphertext, they can't tell whether that ciphertext was correctly constructed. It's possible that an adversary could send a malformed ciphertext and try to use that to learn information about the secret key. And this isn't just a hypothetical. This is actually possible because of the search decision equivalence I mentioned before. I don't want to go into the details of that, but it really can lead to real attacks. And there are several places where this attack has been described. So in some settings, this IND-CPA secure encryption scheme is safe to use. Scenarios where we believe the adversary is passive. But if we're worried about an active adversary, and in some cases we are, we need this stronger security notion, chosen ciphertext attack security. And we can achieve a scheme like that. We can take our CPA secure scheme and apply an appropriate transformation, and that will get us to a chosen ciphertext secure scheme. And there are a variety of ways of doing that. So this is public key encryption from the learning with errors problem. From public key encryption, we can then go to key exchange or key agreements. And there's a fairly long history on this problem. People originally started off with public key encryption, and I've listed the public key encryption schemes on the left from LWE and ring-LWE. And then people started talking about ring-LWE. People started talking about approximate key exchange, and then exact key exchange. And there are a few different techniques for achieving exact key exchange, but one of those is based on error correction or reconciliation. And so I just wanted to show you how we can turn public key encryption from the previous slides into key exchange. Okay. So here's the idea for a basic learning with errors key agreement protocol. Okay. So we're going to have a public parameter A. This is our blue matrix A. Okay. Alice, she's going to prepare her message by picking a small random secret S and E and computing her message B, AS plus E. Exactly as we've done throughout the presentation so far. Okay. And then Bob, he's going to do exactly the same thing on his side. Well, he'll do the transpose, but more or less exactly the same thing. Okay. And then from these two values, they compute their approximately equal shared secret, just as we saw for public key encryption. So at the heart of the public key encryption scheme I showed you, there's really a key exchange algorithm going on. Okay. Now, of course, as I mentioned, these shared secrets are only approximately equal, and so we need some kind of rounding or error correction. Okay. And I showed you how rounding worked for public key encryption. For a key exchange, we have to do something slightly different, still roughly the same idea. I'm going to mention a technique due to Ding and to Peikert. So the technique I showed you before, this basic rounding technique, said that we're going to round our values to either 0 or Q12. Okay? So if we have something that's closer to Q12, we treat that as a 1. And if we have something that's closer to a 0, we treat that as a 0. Now, this worked for public key encryption, but it turns out it's not really going to work for key exchange. We'll get a non-negligible probability of failure of one party rounding the wrong way, and it's sufficiently large that it won't allow us to come up with the same key on both sides. So we need a slightly different rounding technique, and I'm going to give you the presentation by Peikert. It's fairly similar, except we're going to divide our number line up into 4 segments. Okay? And Bob, the second party, is going to send an extra hint to Alice. Bob's going to tell Alice which of the 2 regions his value was in, either the green region or the red region. And then Alice will round slightly differently based on Bob's information. If Bob says his value is in the green region, then Alice will round like this rule says here. Whereas if Bob says that his value is in the red region, Alice will round like that. Okay? Just a small change, just one extra bit of information from Bob to Alice. And this allows us to achieve rounding correctness with much higher probability. Okay? Basically, we can show that if Alice's value and Bob's value are close enough to each other, namely with Q on 8, then this is always going to work. And basically, it's because Bob, if he says his value is in the green region, and he rounds to 1, say, then when his value is in that region, Alice's value will be correctly rounded as long as her value is in any of the green regions on the far right. Yeah. So we can improve the error rate, improve correctness, and achieve what we need for key agreement. Kind of like how error correction in QKD helps, except here we're doing error correction modulo Q rather than binary error correction. Yeah. And conveniently, the security isn't affected. So Bob does leak this information, whether his value is in the green region or the red region, but that actually doesn't tell an adversary any information about the secret key that they agree on. Okay. And so coming back to our key agreement protocol now, we have what we had before, Alice and Bob sending their B and B prime, and Bob sending this additional information about rounding. And that will allow them to compute an exactly equal shared secret. And this is the LWE version, and the ring-LWE version is very similar. We just have ring elements instead of matrices and vectors. Now, to turn this into a practical key exchange protocol requires a little bit more work. So on this slide here, I'm showing you how we've modified that to create a protocol called Frodo. This is called Frodo because it's based on plain LWE. It doesn't use the ring. That's what passes for humor in my circles. There's a trend in post-quantum cryptography to name things after science fiction and fantasy franchises. So there's a ring-LWE protocol called NewHope because it was more efficient. It was a new hope for post-quantum key exchange. And then Frodo doesn't use the ring. And there's some other ones based on Kyber crystals from Star Wars and dilithium crystals from Star Trek. We're very nerdy. Anyways, sorry. So Frodo LWE key exchange. So it's quite similar to what we saw on the previous slide, just a little bit more detail that we need in order to actually carry this out in practice. So for example, rather than generate a very large matrix A and send the entire matrix over, it suffices for us to pseudo-randomly generate A. So we only have to send a small seed value over. Okay? Our public key here is, again, B equals AS plus E, except it's actually in a matrix form rather than a vector form. Okay? And our shared secret, V, is actually a matrix calculation rather than just a vector calculation. And that allows us to obtain a little bit more efficiency. But by and large, it's exactly the same basic protocol that we saw earlier, and all going back to the key exchange that's present inside the original lattice-based public key encryption scheme. And we can show that this key exchange algorithm is secure if the decision learning with errors problem is hard, with the same type of proof for the theorem I mentioned earlier. Now, like I said, there are a few extra details going on here. So we have to do a little bit more sophisticated rounding. Rather than just rounding out 1 bit, we actually round out 4 bits. That achieves greater efficiency. We have to say what the error distribution is in practice. We don't actually use a Gaussian distribution. We use something that's sufficiently close to a Gaussian distribution by a measure called Renyi divergence. And by using this special distribution, we make it more efficient to sample. But it all still holds with the same security. Okay. And one of the ways we find all of these parameters is by search scripts. So many of the proposals for this have optimization scripts that search across the many different parameters, because we have the size of the matrix, we have our modulus, we have our error distribution, and all of these have to achieve certain levels of security and correctness. So we just plug all of those into a script, and we get some parameters out at the end. And for example, the parameters we got for Frodo achieve this level of security. So based on our best known attacks, we have 144-bit security against classical adversaries, 130-bit security against quantum adversaries, with matrices of size 752 by 8. Okay? And this results in total communication, 22 kilobytes summing Alice and Bob's messages together. And a failure probability of around 2 to the minus 39. So with probability 2 to the minus 39, rounding will not work, and they'll get different values. For many scenarios, 2 to the minus 39 is sufficiently small. Network packets on the internet are lost with probability much higher than 2 to the negative 39. I've also mentioned a third measure of security here, this so-called plausible lower bound. And this plausible lower bound is based on the idea that all of the known algorithms for solving the lattice problem require creating a list of vectors. And so if that list of vectors is sufficiently large, and it's plausible that all algorithms might require creating vectors that large, then that could give us a lower bound on the possible runtime. And so from that approach, this parameter set would have 100-bit security. We did a few different parameter sets, in fact, so we can achieve higher security level, 128-bit plausible lower bound, 160-bit quantum security with just a few extra kilobytes in communication. So that was for learning with errors algorithm. We can also have ring learning with errors-based key exchange. Here's one algorithm called the BCNS algorithm. And again, it has exactly the same pattern as we saw before. There's an AS plus E operation to create a public key B. Bob does the same thing on his side. They compute a shared secret or an approximately shared secret, and they have some error correction. Okay. And again, from this type of protocol, we can pick parameters. And here's one plausible set of parameters that achieves 80-bit quantum security and about 8 kilobytes of communication. Okay. So this BCNS protocol that I just mentioned isn't actually the state of art in this scheme anymore for ring-LWE cryptosystems. The state of the art is probably one called NewHope that was presented in 2016. It used different parameters, a different error distribution, and achieved quite good performance. And it's been improved upon since then. But NewHope got a lot of attention, not just because it had a much cooler name, but also because it was implemented and used. So Google did an experiment involving NewHope in their Chrome browser. Chrome has a few different versions. There's something called Chrome Canary, which is kind of like an alpha version of Chrome. And so in 2016, the Google folks did an experiment where they implemented NewHope in TLS in a cipher suite they called CECPQ1 to test and see whether anything would break. They didn't deploy it to the billions of users who actually use the main Chrome, but they did deploy it to thousands of users that use the Canary version. They ran it for a few months, and basically there were no problems. So Chrome Canary browsers talking to Google servers could successfully negotiate and use this post-quantum protocol. And while that may not sound surprising, but the web ecosystem is actually quite complex. And even if a browser and server are talking the same protocol, there are often proxies or filtering boxes in between that can break things. But they didn't really notice very many problems. And so it seems like the path to deploying it is not too fraught, at least for TLS. Now, we've done some evaluation on the different post-quantum algorithms to try to get some idea about their different performance characteristics. So I want to tell you a little bit about that. So I'm going to talk about the evaluation of a few different algorithms, some of implementations that I've been involved in for ring-LWE and LWE. Compare that with a variety of other algorithms, RSA and elliptic curve Diffie-Hellman, which are not post-quantum secure, but still provide a very good baseline of performance as they're widely used today. And then a few other post-quantum algorithms. Two other lattice-based ones, the ring-LWE NewHope and the NTRU crypto system, as well as an isogeny-based one, based on elliptic curves. So here's the relative performance of these different algorithms. So in gray at the top, we have our traditional non-post-quantum algorithms. In green, we have a code-based system called McBits. In light blue, we have the ideal lattice problems, ring-LWE and NTRU. In dark blue, we have our generic LWE problem. And then in orange, we have our elliptic curve isogeny problem. Now you can see for the traditional crypto systems in gray, they have a really good performance and trade-off in terms of both speed and communication. They're very fast in software, and they have very small communication. And none of our post-quantum candidates to date achieve quite that same performance on both characteristics. We can have very fast post-quantum crypto systems, but at the expense of having larger public keys, in some cases very large. So you can see our code-based crypto systems can be quite fast, but have very large public keys, around 300 kilobytes. Our ideal lattice systems in the middle of the table probably have the best performance trade-off. They're quite fast, and they are larger than RSA and elliptic curves, but they're not too much larger, 1 to 4 kilobytes of communication round trip. Okay. LWE is a bit larger. Our smallest post-quantum crypto system, elliptic curve isogenies, is unfortunately much slower than the other ones, between 15 milliseconds up to 300 milliseconds, 400 milliseconds for a non-optimized implementation. Okay. So this is why post-quantum crypto isn't quite a slam dunk yet. We don't have good performance for small communications and high speed quite yet. This is for key exchange. If we switch over to signatures, which I haven't really said much about at all, the situation is also difficult for post-quantum algorithms. So here I've got 3 different families, hash-based signatures in red, lattice-based signatures in blue, and elliptic curve isogeny signatures in orange. And again, you can see that sizes are not great. I haven't even put speed on here. I've just put public key and signature size. And for most of our post-quantum schemes, the public key or signature size is quite large. The smallest one, I guess, we have for stateful hash signatures around 4 kilobytes. But lattice-based schemes larger than that. So it's a challenge to build post-quantum authentication. So this makes the transition to post-quantum crypto not entirely trivial. Okay? And it's important to start making this transition relatively early. I mentioned to you the timeline at the beginning, that we want to make sure we have algorithms in place before quantum computers are available. But in fact, we might want to have algorithms in place well before that. And that's due to the problem of retroactive decryption. So a passive adversary who records communication today can decrypt that in the future once they get a quantum computer. Okay? So if you have anything that's encrypted today using elliptic curve Diffie-Hellman or RSA, in 30, 40 years, when there's a quantum computer, someone can retroactively decrypt that. And we know that people are recording ciphertext today. At least at one point a few years ago, there was indications from the Snowden documents that the NSA was recording all encrypted communication on the internet. Whether that's, I mean, it's grown a lot since then, so whether they're still able to do that, we don't know. But there is, a lot of information that's encrypted that's being recorded for later decryption. Now, in some scenarios, this isn't a problem, but in some scenarios, this is a problem. And so part of the transition to public key post-quantum crypto will be to provide potential post-quantum security to early adopters. And one way people are proposing to do this is in the form of what are called hybrid cipher suites. The idea being that we'll use both pre-quantum and post-quantum algorithms together. And this would be secure as long as one of the algorithms is unbroken. Okay. So why would we do a hybrid crypto system when we could just use post-quantum algorithms directly? Well, this provides potential post-quantum security, but with backwards compatibility and with compliance with existing standards. So if you've done any work on QKD certification, you might have heard of FIPS certification. FIPS is a US government standard that says how US government systems should encrypt information. And QKD is not FIPS certified. So in fact, systems today that deploy QKD, but we want to remain FIPS certified, actually use public key crypto to derive a FIPS certified key, and then XOR that key with a QKD-derived key to maintain FIPS security while still achieving the security that QKD provides. We could do the same thing in post-quantum crypto. We could take our traditional systems, which are FIPS certified, and combine them with a post-quantum crypto key to obtain potential post-quantum security, but maintain standards compliance. This also reduced the risk of us having gotten the post-quantum algorithms wrong. So we haven't studied the problems for post-quantum cryptography as well as we have studied factoring and discrete logarithms. So there's the potential that we don't have the parameters quite right and that there could be significant cryptanalytic advances. If someone just used post-quantum algorithms today and we used them with poor parameters, it would be quite unfortunate if they actually undermined security because we didn't understand those problems as well as we would like. So that's why people are talking about using hybrid crypto systems. Now, if we're going to use hybrid crypto systems, it's important to consider backwards compatibility as well, even for systems that are non-hybrid aware. That was part of what the Google experiment was about. So if we're going to move to hybrid cryptography, at least as a transition path, there are 4 possible stages we could go through based on the type of key exchange we use and the type of authentication we use. So we could start off with hybrid key exchange, where we use traditional and post-quantum algorithms, but still use traditional authentication. Okay? And that's what Google did in their example, and what we've done in a few studies as well. We might then move on to using hybrid authentication and eventually switch over to solely post-quantum algorithms. My opinion is that this first option here is the likely focus for the next 10 years. And we'll start seeing early adopters do this exact thing here. And there are 2 reasons for that. One is that we don't actually need post-quantum authentication for secure channel establishment for quite a while. Okay? A future adversary can retroactively decrypt. They can retroactively break confidentiality and if they can recover the secret key. So that's why we need post-quantum key exchange. But they can't retroactively be a man in the middle. They can't retroactively break authentication. So post-quantum authentication is not so important for channel establishment until we have quantum computers. So that's one reason I think this will be the focus for the next 10 years. The other reason is that transitioning the public key infrastructure, certificates, seems to take much longer. We have multiple parties in the ecosystem that need to be on board with this, certificate authorities, rather than just browser manufacturers. So Google or any of the browser vendors could immediately deploy post-quantum key exchange if they wanted to, but they have to wait for certificate authorities to decide to adopt new signature algorithms. And we've seen examples with elliptic curve cryptography on the very slow speed of CAs making this transition. So I think the first option will be our focus. So we can take a look at existing protocols like the TLS protocol and think about how to do that. So you could try to create a new Diffie-Hellman type cipher suite with a new key exchange method for hybrid cryptography. Now we need to do a little bit of engineering to make that happen. So we have to figure out how to change the message formats to convey both an elliptic curve public key and a post-quantum public key. And there are a few different ways to do that. And we have to compute a shared secret using both of these keys. Again, a few different ways to do that. And there are a few different proposals already. So the standards communities are starting to think about this. For TLS 1.2, the current version of TLS, there have been several papers and prototypes. I've been involved in a few of these. There's the Google experiment. And all of these prototypes have shown us that we basically don't have any backwards compatibility problems. As we're looking at these experiments, we should also think about performance, because we're doing more cryptography, and that's going to decrease performance of our systems. So we did one experiment on measuring the throughput of TLS with hybrid cipher suites. So in this graph here, what I'm showing you on the y-axis is the number of connections per second at a web server. And on the x-axis, we're seeing the size of the web page being downloaded, from 1 byte up to 100 kilobytes. Okay. So the more connections per second, the better. So higher is better on this graph. And the first line you can see is the throughput if you're just using plain elliptic curve cryptography like you use on the internet today. Okay? And for, say, a very small web page, you can see that the web server can support, say, 1,200 connections per second. Okay? If we make it a hybrid cipher suite, say we add NewHope key exchange in based on ring learning with errors, we have 2 key exchanges going on, elliptic curve Diffie-Hellman and ring-LWE. And you can see there is a small performance penalty, but it's not too bad, about 8% in terms of decreased throughput. And we have other algorithms shown here that do more significantly impact throughput, but not too badly. It's not going to ruin the internet if we have to use any of these algorithms right away. Okay. So the situation isn't too dire. Now, the last thing I want to talk about is a project that I'm involved with on creating prototypes of post-quantum crypto that we call Open Quantum Safe. This is a joint project with Michele Mosca at Waterloo and a few others. So this is an open-sourced library. You can download it on GitHub, where we've collected together a variety of post-quantum algorithms in C. And we structured them with a common API. Our library builds on x86 architectures as well as ARM, so it can be compiled on a Raspberry Pi, on Android, or on any of our desktop systems. And it collects together a variety of post-quantum implementations. So our software that we've written, or wrappers around existing open source implementations, as well as contributions from others. And the goal of this library is twofold. We want to be able to enable direct comparison of implementations, similar to the EBAX or SuperCop benchmarking system. But we also want to be able to support testing of these implementations in other software. So we're able to do prototype integrations of these algorithms very easily into application-level protocols. And because we're using a common API, people can reuse our library to test out new algorithms in software. And that's how we did the experiment I showed you on the previous slides about throughput, as well as some other timing experiments. So in our library, we have an API for key exchange, as well as for signatures. And underneath that, we have a variety of different primitives. One's based on ring-LWE, LWE, and so on. And on top of that API, we have several different applications we've integrated our API into. The most important one so far has been OpenSSL. This is a widely used open source implementation of the SSL TLS protocol. And it's the one that's used in the Apache web server, for example. So it powers a large number of systems. In our library today, we have 10 key exchange algorithms from a variety of different primitives. And we're just getting started on signature schemes. We have a symmetric signature scheme called Picnic, and we're working on adopting a few others. And once the NIST process starts seeing submissions become public, we're hoping to integrate more and more of those into our library as well. In our library, we can do benchmarking, so we can do performance evaluations for runtime, like I showed you on the tables for key exchange performance. We can also do memory usage benchmarks for measuring the performance, the memory performance on small systems. But the other key component of our library are these application integrations. Like I said, we've integrated into the OpenSSL library. So this means we can do SSL cipher suites using key exchange from liboqs, our library. And this is allowing us to successfully do post-quantum key exchange in the Apache web server, as well as other applications. Someone emailed us out of the blue saying that they'd used this in OpenVPN, which is a virtual private networking software, and they just directly used it with no modifications to the library whatsoever. So it was really made it easy to prototype these post-quantum algorithms. We're working on integrating this into OpenSSH to be able to demonstrate secure shell login from using post-quantum algorithms, and that's being done with some help from some colleagues at Microsoft Research. So just to bring us to the end, so I've tried to give you a bit of a flavor of the post-quantum side of quantum-safe crypto. These 5 different families of post-quantum assumptions, hash-based, code-based, multivariate quadratic, lattice-based, and elliptic curve isogenies, and in particular talked about lattice-based cryptography, the learning with errors problem. It's important that we get this done with efficiency so that we are ready with the NIST standards by the time we have quantum computers. So I'll leave you with a few links to some survey papers, some software. Slides are up on my website. Thank you very much for your time and for your attention, and I'm happy to take any questions you have.